This is the schematic diagram that I'm currently using for my selective amplifier with a third overtone 10 MHz crystal. I have arrived at this solution for the second stage. No longer a current feedback from the source, but I'm using capacitive feedback by use of the gate drain capacitance and an inductor in the source to provide a suitable, hopefully, feedback, noiseless, from the second amplifier to load the drain of the first amplifier to get a low impedance for the crystal. I'm using an interferometer, this which you can see in the previous video, and I'm using it to balance the carrier. And I have a switch here by which I can switch out one of the legs in the interferometer and set the signal level. And now I'm setting it 40 decibels below the full carrier. And that makes the noise stand out 40 decibels better, so I can rapidly see the noise added by the amplifier. For that I'm using the wideband input here, and then I'm doing experiments on the second amplifier to see what happens to the sideband noise. I have tried different numbers of turns on these coils, ended up with 14.5 and 12 turns. Also different transformation ratios on the output and different values for the inductance in the source. All these things interact in a complicated way, and it's very difficult to find what is the optimum. And further, when I try to increase the gain, because the gain is too low, I get oscillations on this J310 collection. So I need to do something else, but first I will show what I obtained with this configuration. I have saved the performance on GIF files so I can evaluate it easily. The coil I have been using looks very much like this one. A thin wire on the middle of a coil with a much thicker wire. Here is the close range phase noise at a 40 decibels offset. And you can see 20 Hertz here, and I read from the scale minus 126 or so, and plus 40, that is minus 166. This measurement doesn't have very good statistics, but it gives an idea. And here is amplitude noise as well as phase noise at a wider frequency separation. And here the offset is 30 decibels, so the flat floor of the phase noise here is minus 177. And the amplitude noise is much stronger. I have plotted the phase noise in this diagram, where I also have state-of-the-art 10 MHz oscillators. The phase noise I have seen starts as a flat line here, and then it is 1 over f up until here, and then it goes steeper up like that. I think that the straight line here is the phase noise of the amplifier, while the steeper slope at here is 1 Hertz is because of modulation caused by the supply voltage to the oscillator. It has a filter, a big filter with 100,000 microfarads and a resistor of 15 ohms. So that's a time constant of 1.5 seconds, and it could well explain why there is some noise modulation. Another possibility is that the two oscillators of my two-channel system have correlated phase noise. They are fed from the same power supply, and that power supply is filtered in a similar fashion. A little bit more capacitance, but much less resistance. So my system sets a limit somewhere at, say, 10 Hertz or so at present. This could be improved, of course, but first I'm interested in the region here and here to see if I can improve that. While I was evaluating different configurations of the second stage, suddenly this kind of events started to appear. You can see here the noise level, the close range, suddenly became significantly higher. And in the baseband window it is even more clear. So something was unstable. After some time I could locate that problem to this capacitor. A capacitor of this type. It's a Teflon isolated small trimmer, plastic trimmer. Here is another problem. You can see the waterfall, the upper part is a little bit brighter, means more noise, and this time it's wideband noise. This was while I was recording those phase noise measurements that I plotted on the paper. So this error is present in that data set. It is not visible at close range, and I don't know how much it actually affects the result, but probably at least 2 decibels. And I don't know where this problem is. I hope I will find it later on. As it turns out, it was very difficult to find the optimum with so many parameters that interact with each other. So I will try to do this optimization one step at a time. And I start with the first, the grounded gate input. And I am sending the signal through the crystal. It means the narrow band input here. And then I am looking with a small capacitor into the network analyzer, as well as with an oscilloscope probe for the voltage on the drain, while loading the drain with resistors from here to here. And then I look at what is the Q and bandwidth at different values of this resistor, always feeding +8 dBm into the unit and looking at the voltage on the drain. It gives me this table without any resistor. I just arbitrarily put 1 megaohm there, and then I compute what is the Q. I measure the Q, 570,000, and then when I put smaller resistors, the Q goes up. And at 50 ohms, it's near its limit at about 1.28 million. And then I can compute the loss of sideband noise performance with the formula related to the Q squared something, and going from 1.28 to 1.21, the loss is 0.4 dB, and that happens at a drain voltage, peak to peak, of about 1 volt. And then I also look at the wide range, and that comes from the power. Optimum power is when I have a match between the load and the output impedance, and that happens to be about 4 kilo ohms. And if I deviate from 4 kilo ohms, there is a loss. And if I go for 1 volt output, I lose about 5 decibels on the wide range. And if I make the sum of the losses, close range and wide range, I find an optimum somewhere around here. And that is at about 2 volts, peak to peak, on the drain. Or a little bit more, perhaps, but I want to put a little bit more importance to the close range than to the wide range. So I will want about 2 volts peak to peak on the drain of the transistors when running 8 dBm input. I have tuned the input to precisely 50 ohms with a very small inductor here and some resistance here. And exactly 50 ohms, it means to exactly the same impedance that my 50 ohm reference has. Here is what I see on the network analyzer. It says 50.6 ohms and 50 ohms, depending on whether I'm on the center frequency or at the side. With 50 ohms on the resonance and 50.6 off resonance, I have this situation: 50.6 into resistors, and the impedance of the crystals is 4.2 kilo ohms. So for the input of 8 dBm, that is 6.3 milliwatts, I put 6.2 into the resistor and 0.075 milliwatts into the crystal, and most of it will heat the crystal and a little bit will reach the transistor. I have arranged the output like this: 4 turns. At this point, the impedance is inductive, leak inductance between, there is a not very high coupling between the coils, so I need a capacitor to tune it to become resistive. And then I load it with 50 ohms. At this time it's the network analyzer. So I'm looking at the drains of the input transistors, and I find 1.4 volts peak to peak. So that's reasonably close to what I expected. The gain through this unit now is minus 11.7 dB, and the Q of the crystal is 1.145 million. Here is the output impedance. It's about 380 ohms on the resonance and some kilo ohms off resonance. So this is where I load with 50 ohms, a big mismatch. But the mismatch becomes even much bigger at some distance from the center. I have added 2 resistors like this, So this way, when looking into the unit, I see 50 ohms. And this point where I want to load by 50 ohms, it looks to 25 ohms in series with another 25 ohm comes from this 50 ohm resistor and the external load. This way I can use the correlation setup, which measures the excess noise, the noise above room temperature that comes out from a 50 ohm source. So here is the output impedance I have now, very close to 50 ohms, so I can trust the values I get from the correlation setup. With those resistors in place, the properties of that selective amplifier is like you see here. Bandwidth is, the Q is 1.14 million, and the gain through the box is minus 17.6 dB. That means that I have minus 9.6 dBm into a 50 ohm load when studying the noise of this unit. I have set this attenuator to minus 40 dB. It means that the signal that goes into the unit now is 40 decibels below plus 8 dBm. I'm using Linrad to collect correlation spectra, correlation mode 1, and I've set the bandwidth to 50 Hz to make the collection fairly rapid. And here is the screen. I have clicked on the signal on the carrier and calibrated the S-meter for it to show 40, minus 39.99 and minus 40.005. And I then click at an offset of, let's say, 4 kilohertz here. And then I have to wait for the correlation average. I will not have to wait for a very long time, but you can see that the green trace here is already not extremely noisy. And a first indication is that the noise floor minus 157 dBc per hertz. And the correlation advantage is something like 13 decibels on top of that. Minus 157 plus 13 means minus 170 dBc per hertz for the total noise. After some time, the green trace is almost flat, and I look at the noise within the selected passband, minus 157.4, and correlation advantage 13.8 or something. This gives me minus 171.2 dBc per hertz for the wideband noise, AM noise plus phase noise. I can expand the vertical scale by clicking here. And I can move it downwards. And then again expand. And now I have 0.2 dB per division. And the green trace is the sideband noise. And at this point it was minus 171.2. And I can see that that value holds all the way until pretty close to the carrier. There are some spurs, but besides those, I have a flat noise floor up until maybe a few hundred hertz. Maybe closer, but I cannot see that here. Now I want to look at the close range, so I have set the bandwidth to 1 Hz. And I have clicked on the signal at 10 MHz. I can see a calibration error on the frequency, which I don't care about. And since I changed the FFT1 parameters, I have to change the calibration. So I did that, and again now I can see -40, because the signal level is still attenuated by 40 decibels below the +8 that I'm designing for. Collection of correlation spectra. Each spectra now takes 50 times more time. Getting the same correlation advantage takes 50 squared, 2,500 times more time. But I'm looking near the center where the noise is much stronger, so I will not have to wait forever. Here is 25 Hz offset. I have not waited quite long enough. You can see the curve isn't so smooth here at 25 Hz. But the noise floor, it is -155.0 dBc per Hertz. That's the white line here. And the correlation advantage 14.8. This is 1.4 decibels worse than the result at 4 kHz. And maybe if I waited long enough, this would be close to 0, the difference. But it's not important to me at this moment. Here is 10 Hz offset. The correlation is accurately computed here. The green trace is very smooth, and that can be seen that the correlation advantage is 10.1, while the theoretical limit is at 18.5. So I have 10.1 or maybe 10.2 to add to what I read from here, which is -154.6. This gives me amplitude noise equal to phase noise at -167.8 dBc per Hertz. Now, comparing with oscillator performance, 10 Hz is here, and 168, that's here. This is very well below what any of the oscillators has. And of course, what I am measuring is not AM or phase noise on a signal at full carrier level. The carrier is attenuated by 40 decibels. So what I'm seeing here is amplifier noise. And I don't see any flicker noise, probably, because the carrier is so weak here. What I will do now is to switch off the carrier completely, while not changing anything in the setup. I have disconnected the Wenzel oscillator, but not switched it off, so you can see the signal leaking into the two channels. Not very strong, but reasonably strong. And it's clear the peak here is not quite at the center. It should be maybe at this point. So I will look at both sides. This is 10 Hz higher in frequency, and here the noise is -154.8, and the correlation advantage is 10 dB. Here is 10 Hz on the low frequency side. And the noise level here is -154.5. Very small difference, but the correlation advantage differs by a little bit more. It's 8.2. So I clearly see a small difference between the upper and lower side on the filter, but the difference is small, so the average 163.7 will be an accurate result for the amplifier noise plus and minus 10 Hz from the carrier. I have now switched off the Wenzel oscillator and I'm running the same resolution. This is just to check that no other 10 MHz oscillator that might be present here is leaking into my receive system. But this seems okay, so I will increase the bandwidth to make measurements faster. I have selected 5 Hz for some coming measurements. And I almost forgot I have to calibrate after changing the bandwidth, so I switched on the Wenzel again and look at the signal level. Comes as 38.8, so I have to change a little bit on the S-meter calibration. And now the S-meter is okay again, showing 40, minus 40 on this reference level that I have. Here is the noise at the center of the crystal filter. The correlation advantage is small, only 4 dB, and the theoretical limit is 14, so I have good statistical significance on this 4.4 dB. And the noise here within the passband, the baseband passband, is minus 152.8. What I see at the center frequency is the thermal noise of the crystal, which is resistive at this frequency, and of course also the noise of the amplifier when looking into that particular feed impedance. I have disconnected the crystal here and connected a 24 ohm resistor from the sources to ground through a decoupling capacitor, 10 nanofarads. And what I see then is this. It is fairly noisy, significantly more noisy than the crystal. So the impedance of the crystal is higher than 24 ohms on the resonance. And if I evaluate here, I see minus 151.6 and correlation advantage 2.2. Here are the noise levels for the crystal and for the 24 ohm resistor. I will try some other resistor values and see what this looks like. Here is the noise for various resistor values, from 24 ohms up to 2 kilo ohms, and compared to the crystal, which I denote with 0 here, the lowest resistance gives plus 3.4 dB, while the highest, 2 kilo ohms, gives 16.6 dB less noise. And without any resistor, that is minus 16.6, much below 2 kilo ohms. Then, without any wideband input, the noise is even 1 decibel lower. And without any wideband means I have disconnected this wideband input. So there is only the resistor through the capacitor to ground from the source in the last case. And of course that is what will happen while running the filter. There could be an advantage to put a reactance on the source, but that will be more convenient to evaluate when the second stage is in place. And if it really will make any difference, that depends on how well the second stage can be used here because the noise I see here in dBm per hertz, that is 10 decibels below room temperature. It means the amplifier must have a noise temperature well below 27 Kelvin. And that is when being fed from a high impedance source, while the amplifier must present a low impedance to the first stage. Here is the phase noise when I'm sending 8 dBm into the crystal input. The level is minus 164 dBc per hertz. And here comes the amplitude noise. And the level is the same, minus 164 dBc per hertz at 50 hertz. What happens at higher offsets would take a long time to find out this way, but I'm interested in the flicker noise, which should be most visible at 50 Hz. I have reduced the signal level by 29.7 dB, and now I find the noise at 50 Hz at minus 142.5, and this is the phase noise. The amplitude noise seems to be very similar. And the imaginary part is far below. So I click here and see AM and FM noise at the same time. And minus 142.5. And at a larger frequency separation, it is about minus 143.5. And that is the wideband noise of the amplifier. At 50 Hz, I probably see a little bit of the impedance of the crystal, which starts to come down to some several hundred ohms or a kilo ohm or so at 50 Hz. At full power, I see here the sum of the phase noise from the Wenzel oscillator that comes through the crystal filter and the noise of the amplifier at the specific impedance I have, 50 Hz off center, and the flicker noise of the amplifier at that separation and the flicker noise of the crystal. At reduced power, I see only the amplifier noise. The others are reduced together with the carrier. So the difference here shows the flicker noise, and it is about 10 dB. Not large, but clearly visible. But whether it comes from the amplifier or the crystal, I don't know yet. And I can note that this noise, which I have computed in dBm per hertz, it fits to the noise I measured while measuring without any signal. I have minus 179, and I have the wideband connected. The wideband input is connected, so I could compare with this number, and the difference is about 3 dB. And whether that is the noise generated by losses in the crystal filter or whether it's something else, I mean measurement errors, I don't think so. I think what I see from here to here is the thermal noise originating in the crystal, and I can infer that the impedance of the crystal is high above 2 kiloohms, because at 2 kiloohms I would have seen minus 177, and I have 179. So this doesn't look in any way peculiar to me. Here is the frequency response again. The sweep is 100 Hz, and from this I can see that the attenuation from center to 50 Hz offset is about 21.3 decibels. You can see from the markers at the center and at the ends of this sweep. The Wenzel oscillator is here. That is minus 157 dBc per Hertz. This gives me minus 178 dBc per Hertz for the Wenzel oscillator. And that should be compared to what I measured here at 8 dBm input. And that was minus 161 dBc per Hertz. So this is 18 decibels below and should be neglected completely. Here is the response through the wideband input while the crystal is also connected. And you can see the gain through this is minus 18 decibels. So when I will send 8 dBm into it, there will be minus 10 dBm on the output. Now I have disconnected the crystal filter, so it's only the wideband input. And it's clear there is some asymmetry on the filter. I mean the output impedance of the filter is a little bit lower on the high frequency side at, let's say, 10 Hz offset. I don't think this matters much, but it is an indication that maybe I should add a reactance here on the sources. But it could be caused also by the wideband input that matches the crystal reactance. So this is something to look at a later stage if it seems to have some influence on the final result, which I don't know yet because that depends on the second stage. I'm now sending 8 dBm into the wideband input and I see the noise at minus 134 dBc per Hertz. This is with the interferometer to analyze the output. So I have suppressed the carrier by 29.7 dB. Now, another thing, when I look at the amplitude noise here, it is much higher. At 50 Hz, it's about here, it's 129.5 or so. Anyway, the gain on the wideband input is minus 16.6 dB. I was surprised by the high level of the amplitude noise, so I replaced the selective, well, no longer selective, I mean the amplifier, with this 16 dB attenuator. And what I see is a much lower phase noise. It is well below minus 144 for the phase noise. The imaginary part and the real part are about the same size. And when I look at the amplitude noise, it's the same. So the noise that I saw was from the amplifier and not from the rest of the interferometer. From here I can see that the crystal presents approximately 75 ohms to the sources, because 50 ohms and 100 ohms here give plus or minus 1.5 dB in the noise level with respect to what the crystal gives. So I have added a 75 ohm resistor from the sources to ground while using the wideband input. And what I see then is this. the noise level is much higher. This is the phase noise. And here is the amplitude noise. So I cannot explain what I'm seeing, but this is the result I had, and the phase noise is what I'm interested in. I have decreased the number of turns here on the drain coil by 2, and then changed this capacitor from about 10 pf to about 30 pf. This seems to have made a small improvement from here 50 Hz to minus 135 for the phase noise to minus 129.5 for the amplitude noise. I have removed one more turn here by using the first tap on the coil. And then I also added 47 pf from here to ground and set that capacitor to minimum. I didn't quite reach resonance, but fairly close. I don't think that affects the flicker noise at 50 Hz, although I think it would affect a little bit the noise at wide separations. The noise at 50 Hz, here, I have the spur visible now, it is minus 138. It's clearly lower than before. This is the phase noise. But the AM noise, that is much higher. It is in the order of minus 129. This is what the coil looks like now, and I will remove 2 more turns, taking away all those taps. Now the total capacitance here is about 75 pf. And I have reduced the number of turns here with 5 in total to get back the gain, because I lost 2 decibels of gain, and that was associated with a higher Q, of course, on the crystal. I had to reduce the number of turns here by 1, so there are 3 turns now. Here is the phase noise, 50 Hz. The little peak here is at minus 134.5. And here is the amplitude noise at 50 Hz, minus 129.0. Conclusion, the phase noise, which was like this to start with, and then became better and better as the Q of the filter became higher and higher, and also the gain through the unit lower. Then when I restored the original gain and Q, I got back to the original phase noise. So it is the transformation ratio and not the LC ratio of that resonator that determines the phase noise, while the amplitude noise seems to be independent. I have reduced the source resistor by a factor of 2, and I saved the result before I did that, so it is in memory. And as you can see, there is no significant change other than a very small shift in frequency, and that's because the time this network analyzer has been running isn't quite long enough, so there is a small frequency drift. When I compute the Q from memory, marker, search and bandwidth, I get 1.1695, and if I compute from data, it is 1.176. And I don't think that difference is significant. I can wait for a second opinion here. I'm running it very slow because the bandwidth is so narrow, so the filter kind of has memory. And it changes a little. With more current and also a little lower drain voltage, the noise has increased significantly. This is the phase noise. And the amplitude noise is minus 127.5. That's also a significant loss of performance. I have tried to vary the source resistor and the supply voltage. It was originally 4.7 ohms, and I put two of them in parallel to get 2.35 ohms. And I also tried a 10 ohm resistor. The influence on phase noise as well as amplitude noise was not very dramatic, so it's not a sharp optimum to look for. But I found an irregularity. So look at the last line, the same supply voltage, but there is more than 1 dB in improvement from here to here. What I did was that I have changed the power supply filter. This is the original thing, 15 ohms and 0.1 farad. And now I have made it like this, with two filter links, and the selection of capacitors is given by my availability to big capacitors with a high enough voltage rating. But anyway, this filter gives a little better suppression for noise around 50 Hz. Now, with a better filter for the power supply, I am repeating one of the old measurements and I see a significant difference. 136.5 for the phase noise and minus 129 for the amplitude noise. I still have 10 ohms on the source resistor and 17.1 volts. It's just like I had here, but the noise is now 2 decibels lower, 134 and here 136, while the amplitude noise is the same. Now that I have discovered that the sideband noise at 50 Hz offset wasn't flicker noise from the transistor, it was caused by modulation from a noise voltage on the power supply. With the lower noise I have now, I have tried to put a big capacitor, 3300 microfarads, in parallel with this resistor, which currently is 10 ohms. And that is to see whether a reduced current feedback on the transistor will have any influence now. It didn't have before. And indeed, the phase noise is degraded. It's now minus 134. And previously I saw minus 136.5. That's 2.5 dB. And I think that is significant. The amplitude noise is now minus 129.8 or so. And it was minus 129 without that big capacitor. Whether it has improved or whether it's just the uncertainty of the measurement, I don't know. there is an uncertainty in how accurately I have adjusted the phase in the interferometer. And of course there is the statistical uncertainty, but that is fairly small. As you can see here is the phase noise, and the imaginary part is down by a little bit more than 10 decibels. And for the amplitude noise, the statistical uncertainty is even lower, is even better. And here are both of the curves again. Now, when I found that the lower impedance here for audio frequencies increases the sideband noise, I want to increase this impedance from 10 ohms. To do that, I need to put a positive voltage on the gate. For that, I have placed all the transistors on a separate little ground plane, which I can glue to the bottom of the box. That is for cooling. And then decouple it with very low inductance capacitors at several points around the periphery of this little ground plane. The reason for this is parallel JFET transistors, these J310, very easily makes oscillators in the VHF range up to several hundred megahertz. And the resonator can be in many different modes in this kind of massive parallelism. So a good ground plane for the gates is a good idea. With many surface mount capacitors around the periphery of this little ground plane, I expect properties in the VHF range to be exactly the same as before, so I don't expect any new oscillations in the 200 or 400 megahertz range. I have had problems with that earlier. I have connected the gates to a 47 ohm resistor to ground and to one of the BNC connectors. And right now on the BNC connector I have a short. So performance should now be exactly the same as before I made this change to the unit. I don't have the big capacitor there, so what I should see is this line, minus 129 for AM and minus 136.5 for phase noise. I haven't really waited long enough, but 136.5 here looks very probable. So I don't wait more. I will look at the amplitude noise also. And it comes here, and it's hard to know where to read it, so I allow the phase noise also. And here I can see minus 127.2 or so. And I should have expected minus 129 according to the paper. I cannot explain that, but there could have been some noise event. I think I will repeat this. The result I see for the phase noise is stable at about minus 136.5, while the amplitude noise varies a bit up and down. I had expected minus 129. Previous time it was a little bit worse, now it is a little bit better. I don't know why that varies, but it seems that I have the expected performance here. I'm sending a weak signal from this audio generator at 80 Hz into the common gates of the amplifier. The signal is attenuated here by 90 decibels. And I see it on the screen here at minus 116. The signal level is 32 millivolts, and that is into a 50 ohm load of the oscilloscope. And I have a 50 ohm system, and there is a termination in the box. So this is what I have. 32 millivolts peak to peak. That gives me 0.00256 milliwatts, or minus 26 dBm. So the level I am modulating with is minus 116 dBm. That's a pretty strong signal. It's high above the thermal noise of the resistors I'm going to use to set the operating point of the amplifier. When I turn on more signal, this is minus 90, and I step in steps of 10 dB. 10, 20, 30, 40, 50, 60, 70, 80, 90. We don't see anything. So I switch on 40 more decibels from the audio generator. Like that. So now the signal is 130 times stronger, and it's clear what I did is essentially frequency modulation and not much AM modulation. The modulation is minus 146 decibels below the carrier for a modulation signal that is minus 116 dBm. I can tolerate minus 190. That is with a good margin from giving any problems, which means I could increase the voltage by 14 decibels, because minus 190 corresponds to minus 160 dBm on 50 ohms, and room temperature is minus 174, so 14 dB, that's 25 times. Now 25 times higher voltage means that the resistance could be the square of 25, 600 times higher. So I can have pretty large resistors without having to worry about thermal noise. With 27 ohms for the sources and a voltage divider 10 kilo ohms to ground and 56 kilo ohms to the power supply, I have the same currents and voltages on the transistors. And I haven't put any decoupling capacitor on the gates, except for the about 1 microfarad that those parallel low inductance capacitors give. Decoupling the base voltage with 1000 microfarads makes a very small difference. I cannot say for sure it's significant, but I think. Here is what I have seen with and without that decoupling capacitor. I have set lower supply voltages now, 15.6 and 11.8 volts. And I can see that the phase noise goes down a little here, but very significantly at 11.8. Then the voltage between source and drain is only 7.9. So the highest voltage seems to be the best so far. The capacitors in the power supply filter, these ones they are rated 20 volts. So I am a little bit careful. I have tried 20.9 and as it turns out now, performance is worse than I had at 20.2. This doesn't look reasonable. I replaced the aluminium electrolytic 1000 microfarad with 10 microfarad tantalum electrolytic. They should have less noise, and indeed I see an improvement now. So using big electrolytics for low noise isn't a good idea, obviously. Not at these impedance levels, at least. I have reduced the source resistor from 27 ohms to 15 ohms and set the supply voltage to nearly 20 volts, which means that I get the same voltage from drain to source as I had here. And as a result, I have significantly more noise. Now, I don't know if this is because of the higher current or because of the smaller current feedback at audio frequencies. A bigger source resistor, now 47 ohms, is significantly better for the same drain source voltage. So it is phase noise minus 137.5, the best so far. This resistor, R1, has been 56 kilo ohms all the way through here, the first 47 ohm resistor for the source. I have decreased it to 33 kilo ohms to put a higher voltage on the gate. And that increases the current, of course. And if I look what happens with a similar voltage between source and drain, I see a similar phase noise. Maybe 1 dB lower. This is not surely within experimental limits. Anyway, the resistors for 27 ohms is this one, metal film. It isn't rated for the power it has been running at the highest currents here, but I think it has been cooled enough anyway. For the 15 ohms and 47 ohms, this is a wire-wound resistor I've been using. I'm a little bit suspicious on whether the wires that are wound on this porcelain body, if they are welded or whether they are just squeezed to the metal at the ends, which could be noisy. So I made a 45 ohm resistor by putting 6 parallel resistors of 270 ohm to make 45 ohms. And I had to place 22 volts over that to get about 15 point a little as had been the reference voltage where performance looks best. And indeed this looks promising, and indeed it looks like I would want more than 22 volts, but this is already 10% above the rating for the capacitors. I have been digging deep into the junk box and found things from maybe 30 or 40 years ago when they thrashed the mainframe computers of the time when power supplies didn't use switch power. So I found capacitors that will allow me to set 30 volts for my unit here, and also with better filtering, larger capacitances. And I also increased this because this voltage rating is 75, so it's very high. And here is what the power supply looks like. 3 big 75 volt capacitors and 6 a little bit smaller 30 volt capacitors. And the resistors with some cooling for them. The result is interesting. I'm running at 22.2 volts like before, but the phase noise is now at minus 138 almost. And the amplitude noise here, I show both of them at the same time so I can easier read. Amplitude noise minus 133. It seems that this new filter gives a slightly better DC supply, minus 133 at this type of voltage. I didn't have that before. Minus 138 almost. Well, 137.5 I have seen before. But now I can increase the supply voltage above 22. I have tried some higher voltages, 25, 27, but that degrades performance. I have also tried higher source resistors and smaller source resistors, but minus 137 is the best I have seen. I have marked all the best results. They all come at a drain to source voltage about 15 volts, 15.8 down to 14.6. Higher or lower gives less good performance, but the result is similar for source resistors from 27 ohms up to 67 ohms. So current feedback at very low frequencies doesn't seem to affect the sideband noise generated by the amplifier. I have restored the configuration that gave me minus 138 dBc per hertz at 50 hertz offset. And I have run it now also with a larger transform size for the correlation FFTs. And I see at 50 hertz here, there is the 50 hertz spur, at minus 137. And I saw that also with the smaller transforms. So I don't know why I saw as good as minus 138 before, but probably that was a mistake caused by not so careful checking of the carrier suppression of the interferometer. Anyway, minus 137, that's what I can reach with this amplifier, and the voltage should be close to 15 between drain and source, but current is not very critical. I have measured Q here and gain through the unit at different currents and voltages. As it turns out, the lowest loss through the unit is at a high power, and the highest loss, about 0.1 dB more, is at the lowest power. This column is power in watts. The Q differs very little it is best at higher power and less good at lower power, but the difference is in the second decimal. This is Q in millions, 1.249 million. So, conclusion is, I don't have to worry about Q or gain. They are very similar for all the different settings I have had, so noise is the factor to look at. I have looked at the voltage ratio, the voltage on this point, the drain of the transistors, and at this point, at the secondary side of the output capacitor. And I have tried it with no load or 50 ohms or 75 ohms, and the voltage ratio is the same. It is 0.325. I want to know the unloaded impedance here, equivalent to know the unloaded impedance here. To that end, I'm looking at this point through a small capacitor. Here I'm sending a signal through the wideband input, and the Q is about 3, and the gain is the same, about minus 18 dB. Here is what I see through a 10 pF capacitor. Q is 94 and the gain is minus 12.5 dB. Now the output capacitor is only 1 pF. Q didn't change much, but the loss through the unit has increased. It's now the gain is minus 31.8, means nearly 32 dB loss. This means that the loading by the network analyzer is now insignificant, and I can check what load I can put on the drain to lose 6 decibels of the signal level. With 12 kilo ohms on the drain, I have lost 6.4 decibels. I have made this coil with several taps on it, so I will try to see whether I can get the same transformation ratio with a higher impedance on the drain. Now Q is here, 1.21 million, and the gain is minus 12. This is with the new coil, and I have selected the tap giving 1.21 million for the Q. When I look through the wideband input with a 1 pF capacitor as the only load on the output, this is what I see, 21.96. That means minus 30 dB. That's the gain of the unit now. And now I have connected a 12 kilo ohm resistor, the same one that I used for the previous coil, and the bandwidth has changed, and the gain. It has increased the loss by a factor of 10, and it was 6.4 on the previous coil. So the impedance on the drain has increased significantly. The sideband noise at 50 Hz is degraded. It's now minus 133. It was 137 before, so it's a loss of 4 dB. Now the gain has increased by 4 dB also, so there is probably an improvement at wide range by 4 dB. But I want better at close range, so I will change the transformation ratio of the output coil. The transformation ratio was about 0.18. I have now changed it by moving to another tap on the coil, so now the transformation is about 0.3. That is more in line with the transformation I had with the previous coil with 2 windings on it, but now the loss through the box is 16 dB, and I think it was 18 before. but I'm not sure. You can see if you look back in this video. Now, with the transformation ratio back at about 0.3, I see the phase noise at about 137.5 here. So this configuration makes the same narrow band, sideband phase noise. But as it turns out, for some reason, the amplitude noise is now significantly higher, at minus 129. I have put back the original coil with 2 windings, and the result now with phase noise is similar as I had before, but amplitude noise is higher. As you can see here, phase noise 137.5, amplitude minus 128.3 or something like that. Here is the configuration I'm using right now. 45 ohms, 22 point a little. It was minus 133 or perhaps minus 132. But now it is much worse. Phase noise, however, is not very different. I have placed fixed capacitors on the taps of the coil, like this. The total number of turns is 16.5, and I have fixed capacitors on taps from 2 up to 7. These capacitors are selected for the tuning. When I tune this capacitor for maximum signal with a 50 ohm load, and then look into the output with the network analyzer, I want to see a very high impedance that is purely resistive. And to obtain that, I have to put these capacitors, and they have to have several different values. And actually, the lowest one at tap number 7 I have never used. And then I measured performance, and here is what I find. Gain goes from minus 2 up to minus 11, and the noise is minus 124 for tap number 2 and minus 138.3 for tap number 6. And that's the phase noise. And the amplitude noise looks normal. And the impedances at tap number 6, the impedance on the resonance is 2 kilo ohms, but off resonance it's 7.5 kilo ohm. So I think with this I have the first stage in a understandable configuration, and I can try the different taps to see what it makes to the total performance when I add the second amplifier. Now, for this to work well, I had to do something that was a bit surprising. I had to remove the DC voltage on the gate. It seems that the capacitor had gone a little bit noisy, that tantalum 2.2 microfarad. So when I removed it and put the same current through and voltage on the transistor, the phase noise became better. It went back to what I found originally when doing this table. I wasn't able to quite restore, and I had this problem with a lot of AM noise. So this is simpler, and I tried first 4.5 ohm here and then 10 ohms, and I didn't really see any difference. One thing that has some influence, however, is this added 0.1 microhenry inductor. It removes the load from this resistor. It doesn't load much because it's coupled through 4.7 pf only, but it makes a significant increase in the unloaded Q at the drain. So there is no disadvantage having this inductor. I also added 3.3 nanofarad here because when measuring the impedance on the sources, I find it is slightly inductive. With this capacitor, it becomes purely resistive at this point. This seems to not have any effect, but I don't see any harm with it either. And I think that is all to say about this. I have measured the gain with the network analyzer directly on the points labeled 2 to 6. But for phase noise, I have this network on the output because the correlation receiver needs to see 50 ohms. Now this video is long enough, so the next amplifier stage will be in the next video in the Nerds series that I'm doing.